What if everything you think you know about time is just a tiny fragment of a much larger, stranger story? Picture the universe not as a single, linear path, but as a vast library, each book a different timeline, each page a moment that could have unfolded in countless ways. Somewhere in those cosmic shelves, there might be versions of reality where dinosaurs never went extinct, where humanity colonized Mars centuries ago, or where you made a single different choice that changed everything. This isn't just science fiction, it's one of the most thrilling mysteries scientists and philosophers are grappling with today. The idea that our universe might be part of a hidden web of alternate timelines isn't just a wild speculation. It's a possibility that could rewrite our understanding of existence itself. So let's take a step into the unknown. Across the cosmos, there are theories, some grounded in cutting-edge physics, others dancing on the edge of imagination, that suggest time isn't what it seems. Maybe it branches like a tree, splits like a river, or even folds back on itself in loops we can't yet see. Some researchers believe parallel universes could be bubbling up every second, while others think our entire timeline might be a shadow of something far grander. And that's just the beginning. From the mind-bending implications of quantum mechanics to the eerie patterns in ancient myths, the clues are everywhere if you know where to look. That's why we're diving deep into 30 of the most fascinating theories about the universe's hidden timelines. We'll explore everything from the scientific to the speculative, the eerie to the awe-inspiring. Could dark energy be the fingerprint of a collision with another timeline? Are black holes gateways to alternate realities? And what if the reason we haven't met aliens isn't because they're rare, but because they're living in timelines just out of reach? Buckle up, because this journey will take you through the multiverse's best-kept secrets, and by the end, you might never look at time the same way again. Imagine standing on the shore of a cosmic ocean, watching bubbles rise endlessly from the depths, each one a universe, each one a reality unlike any other. That's the heart of the eternal inflation model, a theory that suggests our entire universe might just be a single bubble in an infinite, frothing sea of space-time. This idea, first pioneered by physicist Alan Guth in the 1980s, turns the traditional view of the Big Bang on its head. Instead of a one-time explosion, inflation proposes that the universe expanded at unimaginable speeds in its earliest moments, and in some corners of reality, that expansion might never have stopped. Here's how it works. Picture space as a vast, unstable energy field, like a hill covered in boulders that could roll downhill at any moment. Most of the universe settled into a stable valley, what scientists call a true vacuum, where energy is balanced and calm. But pockets of this field might still be trapped in a false vacuum, teetering on the edge, ready to release their pent-up energy. When one of these pockets finally tips over, it triggers a new burst of inflation, birthing an entirely new universe with its own laws of physics, its own timeline, its own version of reality. And this isn't a one-time event. It could be happening endlessly, creating an infinite multiverse where every possible outcome plays out somewhere. The implications are staggering. If eternal inflation is real, then somewhere out there, there's a universe where gravity is twice as strong, where time flows backward, or where life evolved in ways we can't even fathom. Some versions of this theory even suggest that black holes could be the seeds of new universes, that every time one collapses, it sparks a new Big Bang in its own hidden dimension. And here's the twist: we'd never know. These bubble universes would be forever separated from ours by the breakneck expansion of space itself, like islands drifting apart in an endless ocean. But how do we even begin to test such a mind-bending idea? Some researchers look for faint imprints in the cosmic microwave background, the afterglow of the Big Bang, which might bear scars from collisions with other bubbles. Others study the fundamental nature of vacuum energy, searching for clues that our universe isn't as stable as it seems. And if they're right, it would mean that every decision, every chance event, every fork in the road of history isn't just a what if, it's a what is, playing out in some other corner of the multiverse. So next time you gaze up at the night sky, wonder, are we alone in this bubble, or is the cosmos far stranger and far richer than we ever dared to dream? What if the end of our universe isn't a final curtain call, but just the first act in an endless cosmic encore? That's the bold vision of the Cyclic Universe hypothesis, championed by Nobel Prize-winning physicist Roger Penrose. In this mind-bending model, time isn't a straight line, it's a vast, repeating loop where universes rise, fade, and are reborn in an eternal dance. And here's the twist: black holes might hold the secret to how information, maybe even fragments of past timelines, leaps from one cycle to the next. Penrose's theory, known as conformal cyclic cosmology, starts with a startling observation. As our universe expands toward heat death, where all matter disintegrates into radiation, something peculiar happens. The equations of physics suggest that this ultra-distant future, cold, empty, and stretched impossibly thin, actually starts to resemble the ultra-hot, ultra-dense conditions of the Big Bang itself. It's as if the final frame of the universe's movie somehow rewinds to become the first frame of the next. Space and time lose their meaning at these extremes, allowing one epoch to blend seamlessly into another. But how could anything survive this apocalyptic reset? That's where black holes come in. These cosmic vacuum cleaners don't just swallow stars, they might also act as cosmic archivists. According to Penrose, the information devoured by black holes over billions of years isn't truly destroyed. Instead, it's imprinted onto the fabric of space-time in faint, swirling patterns called Hawking points. When the next universe blossoms from the ashes of the old, these ghostly fingerprints might reappear as mysterious bursts of energy, like cosmic breadcrumbs left by a previous reality. Some researchers even speculate these echoes could contain traces of civilizations long gone, their stories encoded in the very structure of the new cosmos. The implications are staggering. If Penrose is right, our universe might be just one page in an infinite cosmic novel, with each cycle subtly shaped by the one before. Ancient myths of eternal return, from Hindu cosmology to Norse legends, could be eerie premonitions of a truth written into the laws of physics. Even more tantalizing, if information can cross between cycles, could the laws of nature evolve over time? Might gravity or the speed of light change slightly with each rebirth, creating a multiverse not of parallel realities but of sequential ones? Of course, not everyone's convinced. Critics argue that without a clear mechanism for how matter could reset between cycles, the theory remains speculative. Yet Penrose and his collaborators claim they've found hints of these Hawking points in the cosmic microwave background, ancient light from the early universe that shows unusual circular patterns. If confirmed, it would mean we're literally seeing scars from a universe that existed before our own. So the next time you hear about the end of everything, remember, in the grand scheme of things, it might just be a comma in a story without end. And if you ever spot an odd flash of energy in the night sky, ask yourself, could it be a message from a timeline lost to time? But what if everything you see, the stars, the planets, even your own hands, isn't truly three-dimensional at all? Picture the universe as a cosmic movie screen, projecting a lifelike illusion from information stored on a distant, two-dimensional surface. This is the heart of the holographic principle, a radical idea from physicist Leonard Susskind that suggests our entire reality might be nothing more than a shadow cast by data encoded at the very edge of the cosmos. And if that sounds wild, here's where it gets even stranger. This theory could mean that time itself is just another layer of the illusion, with every moment we experience being a single frame in a vast, higher-dimensional hologram. The idea builds on a startling discovery about black holes. When matter falls into these gravitational monsters, it doesn't just vanish. It leaves behind an imprint on the black hole's event horizon, the point of no return. Scientists realized this surface somehow preserves all the information about what fell in, like a cosmic hard drive. Susskind took this further, proposing that if a black hole's surface can encode three-dimensional information in 2 dimensions, maybe the entire universe works the same way. Imagine a gigantic sphere surrounding everything we know, with every event, every particle, every vibration of light etched onto its surface like ink on parchment. Our reality, then, would be a projection, a hologram unfolding from that hidden code. Now, let's twist this into the realm of hidden timelines. If the universe is a hologram, then time, as we experience it, might just be one slice of a far richer structure. Think of it like flipping through a stack of transparent sheets, each one showing a slightly different image. When you lay them flat, you see a single picture, your now. But tilt them just right, and you glimpse other versions, other moments, other possibilities. In this view, alternate timelines wouldn't be separate universes. They'd be layers of the same hologram, all existing simultaneously in a higher dimensional space we can't perceive. This raises spine-tingling questions. Could déjà vu be a glitch in the projection, a fleeting overlap with another sheet in the stack? Are black holes not just cosmic trash compactors, but portals where information leaks between layers? And if our reality is ultimately just data, does that mean the universe is, in some sense, computable, a simulation running on the ultimate cosmic hard drive? Some researchers even speculate that anomalies in the cosmic microwave background, the faint glow from the Big Bang, could be signatures of this underlying code, like pixels peeking through the illusion. Of course, not all physicists are convinced. Critics argue that the holographic principle, while mathematically elegant, lacks direct experimental proof. But supporters point to cutting-edge experiments with quantum computers, where information behaves in eerily holographic ways, as potential clues. And if they're right, it would mean that every choice, every parallel reality, every hidden timeline is already written, not in the stars, but on a 2-dimensional surface so far away we may never reach it. So the next time you watch a sunset or feel the weight of a decision, remember, you might not just be living in a universe, you could be living in a projection of one, a flickering hologram where past, present, and future are all just angles of the same impossible light. Now imagine this: every time you make a choice, whether it's turning left instead of right, ordering coffee instead of tea, or even blinking your eyes, the universe splits in 2. One version of you lives out the consequences of each possibility, while another version walks a completely different path, unaware of the road not taken. This isn't a metaphor, it's the many worlds interpretation. Physicist Hugh Everett's radical vision of reality, where every quantum event spawns an endless tapestry of parallel universes. Unlike the bubble multiverse or holographic projections, this theory suggests that alternate timelines aren't distant or separate, they're unfolding right alongside ours, invisible but infinite. The math behind this is both elegant and unsettling. At the quantum level, particles exist in a haze of probabilities. An electron might be here or there until observed, like a coin mid-spin. Traditional physics says observation collapses these possibilities into one outcome, but Everett flipped the script. What if every possible outcome happens? The coin lands heads and tails, each result branching into its own universe. Over time, these tiny quantum choices snowball, creating a multiverse where every conceivable variation of history exists simultaneously, a cosmic library where every what if is answered with "it happened." This leads us to one of the most chilling thought experiments in physics: quantum immortality. Picture a hypothetical device linked to a radioactive atom that has a 50% chance of decaying within 1 minute. If it decays, the device kills the observer. If it doesn't, the observer lives. According to many worlds, both outcomes occur. but from the observer's perspective, they can only experience the timelines where they survive. In branches where the observer dies, their consciousness ends, but in every other universe they keep waking up minute after minute, seemingly cheating death through sheer probability. It's not true immortality, just the eerie illusion of it, as you only perceive the threads of reality where you persist. Critics argue this is less science and more philosophy. After all, we can't observe these branching worlds. But supporters point to quantum computing, where particles do seem to explore multiple states at once, as potential evidence. And if Everett was right, it means somewhere out there, a version of you is living every path you didn't take, some triumphant, some tragic, all equally real. So the next time you hesitate at a crossroads, remember, in some unseen corner of the multiverse, you didn't hesitate at all. Picture waking up one day with all your memories intact, your childhood, your first love, your last meal, only to realize none of it ever really happened. You're just a momentary spark, a self-aware accident floating in the void, conjured into existence by pure chance. This is the nightmare scenario of the Boltzmann brain paradox, a theory so unsettling that even physicists debate whether confronting it means questioning the very nature of reality. The idea traces back to 19th century scientist Ludwig Boltzmann, who proposed that entropy, the inevitable march toward disorder, might not be uniform. In an almost endless universe, random fluctuations could occasionally create pockets of order. Most of these would be insignificant, a gust of wind here, a ripple of warmth there. But given enough time, even the most improbable events become inevitable. So what's to stop entropy from randomly assembling a fully formed, self-aware brain, complete with fabricated memories, convinced it's lived a full life? Statistically, these Boltzmann brains should outnumber real, evolved beings like us by an unimaginable margin. And here's the kicker: if that's true, how do we know we're not one of them? This isn't just abstract philosophy. Modern cosmology intensifies the paradox. If the universe continues expanding forever, approaching absolute coldness, the era of stars and galaxies will be a fleeting blip in an eternity of darkness. Yet in that endless void, random fluctuations could keep spawning temporary consciousnesses like embers sputtering in ash. Some versions of quantum mechanics even suggest these brains might pop into existence more easily than entire universes, making them the most likely observers in the grand scheme of things. So why does reality feel so stable? Why do the laws of physics seem consistent instead of flickering in and out like a faulty light bulb? Critics offer two escape routes. One appeals to the anthropic principle. We don't observe Boltzmann brains because conscious entities like us can only exist in orderly, low-entropy environments like the early universe. The other suggests the paradox reveals a flaw in our assumptions. Perhaps the universe isn't infinite, or entropy behaves differently at cosmic scales. But the most haunting possibility remains. If Boltzmann brains are inevitable, then every moment you remember, every person you love, every law of nature you trust could vanish in an instant, replaced by a new fluctuation with no past and no future. So the next time you feel deja vu or wake up grasping at a fading dream, ask yourself, is this continuity real or just the temporary coherence of a mind that hasn't yet dissolved back into the chaos? What if the reason we haven't found the edges of the universe is because there aren't any just lines of code in a cosmic computer running our reality? This is the spine-chilling premise of the simulation hypothesis, a theory made famous by philosopher Nick Bostrom that flips our understanding of existence on its head. His argument, known as Bostrom's trilemma, presents three stark possibilities. Either civilizations always go extinct before developing simulation technology, they choose not to run ancestor simulations, or we're almost certainly living in one right now. And when you crunch the numbers, the third option starts to look unsettlingly plausible. Bostrom's reasoning hinges on scale. Imagine a future civilization with computing power billions of times beyond ours. If even a fraction of them decided to run detailed simulations of their ancestors, the number of simulated minds would dwarf the number of original biological ones. Statistically, you're far more likely to be one of those simulations than a flesh and blood human in the base reality. It's like realizing you're probably not the first person in line at an amusement park. You're somewhere in the endless crowd behind them. Now here's where hidden timelines creep in. If our universe is a simulation, then glitches in the system might occasionally bleed through. Deja vu could be moments where the simulation loads a memory incorrectly, briefly showing you a scene it's about to render. The Mandela Effect, where large groups misremember historical details, might stem from patches or updates altering the codebase. Some researchers even speculate that quantum indeterminacy, where particles behave unpredictably until observed, is simply the simulation conserving processing power by only rendering what's being watched. But the most tantalizing possibility, these anomalies might not just be bugs, they could be overlaps with other instances of the simulation running parallel timelines. Picture a cosmic programmer tweaking variables to test different historical outcomes, one where the dinosaurs survived, another where Rome never fell, a third where you took that job offer last year. Occasionally, data might leak between versions, creating false memories or impossible synchronicities. Ancient texts describing prophetic dreams or sudden changes in reality start to sound less like mythology and more like user reports from an imperfect system. Critics dismiss this as unfalsifiable speculation. After all, how could we ever prove we're in a simulation from the inside? But proponents point to potential signatures in the fabric of reality. Some suggest looking for pixelation effects at Planck scale, the smallest possible units of space-time. Others propose hunting for computational shortcuts in quantum mechanics, like the universe cheating by not calculating unobserved phenomena in detail. A few even argue that finding an upper limit to complexity in physics, a maximum energy state or minimum length, would hint at finite processing power. Whether you find this idea terrifying or exhilarating, it forces a profound question. If we are living in someone else's simulation, does that make our joys less real, our struggles less meaningful? Or does it mean that every choice, every hidden timeline, every alternate version of you is just as valid lines of code in a cosmic story too vast to comprehend? The simulation hypothesis doesn't just challenge what we know about reality. It asks us to reconsider what reality even means. Most of us think of crystals as frozen, unchanging structures, diamonds locked in perfect symmetry, snowflakes preserving their delicate patterns. But what if some crystals aren't frozen in time at all? What if they're built from time itself? That's the revolutionary idea behind time crystals, a bizarre form of matter first proposed by Nobel Prize-winning physicist Frank Wilczek. Unlike anything else in nature, these structures don't just exist in space, they pulse, oscillate, and repeat their patterns eternally without energy, like a clock that ticks forever without ever being wound. And if they exist, as recent experiments suggest they might, they could rewrite our understanding of time's hidden architecture. Time crystals defy the most fundamental laws we know. Normally, if you nudge a system, a pendulum, a planet, even an electron, it eventually settles into equilibrium, its motion fading to stillness, but time crystals break this rule. When gently disturbed, they don't wind down. Instead, they lock into a rhythm of their own, oscillating at a frequency unrelated to the energy put in. Imagine tapping a guitar string and hearing it strum itself forever at a tempo no one taught it. That's the eerie magic of these structures. They're not perpetual motion machines, they don't create energy, but they resist the universe's relentless pull toward disorder, dancing endlessly in a groove carved into the fabric of reality itself. So how does this tie into hidden timelines? Wilczek himself speculated that time crystals might be more than laboratory curiosities. They could be cosmic relics, fragments of deeper temporal layers frozen into matter. Picture an ancient tree's rings, each one preserving a record of seasons long past. Now imagine if certain materials under extreme conditions could similarly freeze rhythms from earlier epochs of the universe, preserving oscillations from moments when the laws of physics themselves might have been different. Some theorists even suggest that black holes or neutron stars could harbor time crystalline structures in their cores, their impossibly dense matter locked into eternal pulses older than the stars. Here's where it gets stranger. If time crystals can exist in multiple stable states, each representing a different frozen timeline, could they act as bridges between parallel realities? Quantum researchers have already created tiny time crystals in labs, coaxing them to interact in ways that hint at this possibility. When two time crystals were brought close together, they spontaneously synchronized as if their rhythms were communicating across some invisible channel. This raises a tantalizing question. If time crystals can remember their rhythms across interruptions, could they also preserve traces of alternate histories? A handful of physicists speculate that under the right conditions, these structures might encode information from branching timelines, like scars left behind by roads not taken. Of course, skepticism remains. Critics argue that time crystals, while fascinating, are still poorly understood, more mathematical oddity than cosmic keystone. Yet their discovery has already forced us to rethink one of physics' most sacred principles, the arrow of time. If matter can beat forever without energy, what other impossible structures might be hiding in plain sight? And if time itself can crystallize, could the universe be littered with clocks ticking silently in the dark, each one marking a rhythm older than existence? The next time you hold a snowflake or gaze at a quartz gem, consider this. Somewhere, on scales we're only beginning to glimpse, there might be crystals that don't just exist in time. They are time whispering secrets from layers of reality we've yet to uncover. Time travel stories usually follow the same dramatic formula: change one event in the past, and the future unravels in unpredictable ways. But what if the universe has a built-in safety mechanism, a cosmic undo button that prevents paradoxes by making sure certain events can't be altered no matter how hard you try? This is the spine-tingling premise of the Novikov self-consistency principle, a theory cooked up by Russian physicist Igor Novikov in the 1980s. It suggests that time isn't just a river you can divert. It's more like a Möbius strip folding back on itself so that any attempt to change the past only ends up fulfilling it. Picture this: you travel back to prevent a tragic accident, only to realize that your very presence in that moment, the distraction you caused, the warning you shouted, was the exact thing that triggered the event in the first place. History doesn't rewrite itself. Instead, it adjusts around your actions like a self-healing wound, weaving your interference seamlessly into the timeline. Novikov argued that the laws of physics simply wouldn't allow paradoxes to happen. If time travel is possible, every journey into the past must already be part of recorded history, every action predetermined to maintain consistency. It's not that you shouldn't change things, it's that you can't. This idea found eerie real-world echoes in the infamous John Titor hoax of the early 2000s. A man claiming to be a time traveler from 2038 appeared on internet forums offering detailed predictions about future events, from civil wars to technological breakthroughs. He insisted his mission was to retrieve an old computer needed to debug systems in his dystopian future. But here's the twist: even if Titor had been genuine, his intervention wouldn't have changed anything. Under Novikov's rules, his retrieval of that computer would have always been part of history, his warnings already factored into the timeline's unshakable script. The changes he claimed to prevent were never changes at all, just inevitabilities. The implications are both comforting and unnerving. On one hand, Novikov's principle removes the fear of grandfather paradoxes. You couldn't accidentally erase your own existence because the universe wouldn't let you pull the trigger. But it also suggests a strange fatalism. If every time traveler's actions are predestined, does free will evaporate the moment you step into a time machine? Some physicists argue this could explain why we've never met visitors from the future, not because time travel is impossible, but because their presence must remain invisible, their influence woven so subtly into events that we'd never notice the seams. Critics counter that this theory feels suspiciously convenient, a way to handwave paradoxes rather than explain them. Yet in recent years, quantum experiments have shown particles behaving in ways that eerily echo Novikov's ideas. In closed time-like curves, hypothetical loops in space-time quantum systems seem to self-correct, avoiding contradictions by always arriving at consistent outcomes. It's as if the universe prefers tidy stories over messy paradoxes, editing reality on the fly to preserve its own continuity. So the next time you regret a choice or wish you could rewrite history, consider this. In a Novikov universe, your mistakes might not be failures at all, just brushstrokes in a painting that was always meant to be finished. History books tell us Charlemagne ruled a vast empire in the late 8th century, bridging the ancient and medieval worlds. But what if those books are wrong, not just slightly mistaken, but deliberately falsified on a scale that rewrote centuries? This is the explosive claim at the heart of the phantom time hypothesis, a theory proposed by German historian Herbert Illig in the 1990s. He argued that nearly 300 years of history from 614 to 911 AD never actually happened. Instead, they were inserted into the historical record through a massive conspiracy involving emperors, popes, and scholars. If true, it would mean entire dynasties, wars, and cultural movements were pure fiction, and we're currently living not in the 21st century, but somewhere closer to the early 1700s. The theory hinges on eerie inconsistencies in the historical record. Illig noticed that during this supposed lost period, architectural styles barely evolved, as if time had stalled. The Gregorian calendar, introduced in 1582, required an adjustment of 10 days to realign with the solar year, but according to Illig's calculations, the drift should have been 13 days if those phantom centuries were real. Even more puzzling, certain astronomical events documented from the period, like eclipses mentioned in ancient texts, don't match up with modern astronomical reconstructions. It's as if someone took a pair of scissors to the timeline and spliced in extra pages without bothering to check the sky. Carbon dating adds another layer of mystery. While radiocarbon analysis generally supports established chronologies, there are odd gaps periods where artifacts seem to cluster at certain dates while skipping others. Skeptics argue this reflects preservation biases or natural fluctuations in carbon production. But Illig's supporters point to these voids as potential smoking guns, evidence of a cover-up where history was literally rewritten by scribes commissioned by Holy Roman Emperor Otto Roman III and Pope Sylvester Roman II. Their supposed motive, to place themselves symbolically in the year 1000 AD, a millennial date heavy with apocalyptic significance, by artificially aging the calendar. The implications are staggering. If the phantom time hypothesis were true, everything from Viking invasions to the rise of Islam would need re-evaluation. Charlemagne, often called the father of Europe, might be a fabricated legend, a political tool used to legitimize later rulers. Even the very concept of the Dark Ages could be a mirage, invented to explain away a chronological glitch. Some fringe researchers take this further, suggesting these missing centuries might not be a clerical error but evidence of something stranger, a timeline reset, a parallel history overwritten, or even a temporal rift we've collectively forgotten. Of course, mainstream historians dismiss this as baseless conspiracy. They note that Byzantine, Chinese, and Islamic records from this period independently corroborate events Illig claims never happened. Dendrochronology tree ring dating shows no unexplained gaps spanning 3 centuries. And why would conspirators add time rather than simply control the narrative of real events? Yet the theory persists, fueled by its unsettling central question: how well can we really trust the past when the keepers of history have always been the powerful? So the next time you read about medieval kings or ancient battles, ask yourself, are you studying facts or echoes of a story someone wanted you to believe? The phantom time hypothesis may never be proven, but it serves as a chilling reminder that history isn't just written by the victors, it might be rewritten by them too. Have you ever been absolutely certain about a memory only to discover the rest of the world remembers it differently? Maybe you'd swear the Monopoly man wore a monocle he never did, or that Nelson Mandela died in prison during the 1980s. He didn't, he passed in 2013. These collective false memories aren't just quirks of the human mind, they might be glitches in reality itself. This eerie phenomenon, dubbed the Mandela Effect, has sparked a chilling theory. What if these discrepancies aren't mistakes at all, but scars left behind when alternate timelines collide? Take the infamous case of the Berenstain Bears. Thousands insist the beloved children's book series was once spelled Berenstein with an E, a memory so vivid they can recall tracing the letters with their fingers as kids. Yet every edition, every copyright record, even the author's own signatures confirm it was always Berenstain with an A. Skeptics brush this off as confabulation, the brain filling gaps with plausible details. But why would so many people misremember the exact same detail in the exact same way? Some researchers suggest these anomalies cluster around cultural touchstones because they're the most likely to reveal discrepancies when timelines merge. Think of it like two rivers joining. The biggest rocks create the most visible ripples. Now, here's where science crosses into science fiction. In 2015, the Large Hadron Collider at CERN restarted at unprecedented energy levels, smashing particles with forces rivaling those just after the Big Bang. Around the same time, reports of Mandela effects exploded online. Coincidence or something stranger? A handful of physicists speculate that these high-energy experiments could, in theory, create microscopic tears in space-time, brief ruptures where alternate realities bleed into one another. If multiple timelines normally branch like tree limbs, these moments might fuse some back together, leaving fragments of conflicting memories in their wake. Quantum mechanics offers a possible mechanism. The many worlds interpretation suggests every decision spawns new universes, but what if under extreme conditions those branches could reconnect? Imagine two versions of history, one where the bears were Berenstein, another where they were Berenstain, collapsing into a single timeline. Most details align seamlessly, but some subtle differences linger like phantom limbs. Even wilder, CERN scientists themselves reported an odd anomaly during early collisions, particles behaving as if they'd already been observed before the detectors registered them. Could these be echoes bleeding through from a timeline where the experiment played out slightly differently? Critics argue this is classic apophenia, seeing patterns where none exist. After all, false memories are well documented. The human brain edits recollections to fit narratives, and viral misinformation amplifies these errors. But proponents counter that Mandela effects often involve trivial details, like the placement of a hyphen in Kit Kat or the number of ridges on a U.S. quarter, precisely the kind of minutiae that wouldn't be manipulated en masse by suggestion. And while CERN collisions are unimaginably powerful on a quantum scale, they're still trillions of times weaker than cosmic events that routinely warp space-time, like neutron star collisions. If black holes don't shred reality, why would a particle accelerator? Yet the mystery deepens when you examine who experiences these effects. Surveys show they're reported disproportionately by people with high cognitive flexibility, those adept at spotting patterns and holding contradictory ideas. Could certain minds be more attuned to detecting timeline shifts, like radios picking up faint signals between stations? And why do some Mandela effects eventually resolve, with consensus memories shifting to match the new version, while others linger as stubborn dissonance? Whether you chalk it up to neuroscience or parallel universes, the Mandela Effect forces a humbling realization. Memory isn't just unreliable, it might be collaborative, a consensus reality we unconsciously negotiate with millions of other minds. So the next time someone corrects you on a misremembered detail, pause and wonder, is it your memory that's faulty, or is the universe itself editing the script? Black holes dominate our cosmic nightmares, unstoppable voids where matter vanishes forever. But what if somewhere in the multiverse their perfect opposites exist? Imagine cosmic fountains instead of drains, places where reality doesn't collapse but erupts. These are white holes, hypothetical twins to black holes that spit out light, matter, and even entire universes instead of swallowing them. And here's the mind-bending twist. Our Big Bang might not have been the beginning of everything, just the explosive aftermath of a white hole in some unseen parent universe. The math behind this is startlingly elegant. Einstein's equations describe black holes so completely that they demand white holes as a symmetrical counterpart. If a black hole is a one-way door into oblivion, a white hole would be a one-way exit from somewhere else, an outdoor wedged permanently open. Matter couldn't enter it, just as nothing can escape a black hole. And while we've never observed a white hole directly, some physicists argue that's because they're not just objects in space-time. They might be entire new space-times, birthing universes like ours in a single radiant burst. This leads to a radical reimagining of the Big Bang. Instead of an unfathomable singularity, our universe could have been forged in the eruption of a white hole from a dying cosmos. Picture an ancient, collapsing universe where matter spiraled into a black hole, only to re-emerge transformed as the primordial fire of our own beginning. In this view, every black hole in our universe might someday blossom into a white hole in another, each one carrying echoes of its parent timeline. It's cosmic reincarnation on a scale that bends the mind, universes giving birth to universes in an endless chain of collapse and rebirth. Evidence for this wild idea might already exist. The cosmic microwave background, the faint glow left from the Big Bang, shows mysterious temperature variations that standard models struggle to explain. Some theorists suggest these could be scars from our white hole's violent birth, imprints of the universe that came before. Others point to dark energy's inexplicable push on cosmic expansion, wondering if it's leftover momentum from that initial eruption, still propelling space apart like the aftershocks of a detonation. But how would information cross between these connected timelines? Quantum physics offers a clue. Black holes don't destroy information, they scramble it, preserving data in tangled forms on their event horizons. If white holes are their mirrors, that information might re-emerge in new configurations, like a shuffled deck of cards dealt into a fresh game. This could mean our universe isn't just separate from its parent, it's a transformed continuation with the laws of physics subtly remixed. Perhaps some particles, some forces, even the seeds of life itself, are cosmic hand-me-downs from a reality lost to time. The implications spiral outward endlessly. If white holes birth universes, then somewhere beyond our cosmic horizon, other realities might be blossoming from the black holes we've observed. And if time flows differently near these extremes, our future could already be someone else's ancient history. It's a humbling thought. We may not be the first universe, and we certainly won't be the last. Just one link in a chain of existence stretching forever backward and forward. Each timeline hidden from the next, yet bound by the unbreakable logic of gravity's deepest secrets. What if the arrow of time isn't pointing in just one direction but two? Picture a river that flows downstream and upstream simultaneously, where every ripple sent forward in time sends an echo backward. This is the radical vision of the Wheeler-Feynman time-symmetric universe, a theory that shreds our everyday experience of cause and effect. Nobel laureates John Wheeler and Richard Feynman proposed that reality might be fundamentally symmetrical, not just in space but in time. In their model, the future doesn't simply unfold from the past. It reaches backward just as powerfully, shaping events through what they called advanced waves. And the strangest part, you might have already felt this two-way flow without realizing it. At the heart of their theory lies a startling twist on electromagnetism. Normally, we think of light as radiating outward from a source, a star shining, a bulb glowing. But Wheeler and Feynman showed that Maxwell's equations work just as well if you imagine light traveling both forward and backward in time. In their symmetric universe, every photon emitted is also a photon absorbed, not just at some point in the future, but as an instantaneous echo from the moment of its creation. It's as if the universe is one vast, self-consistent conversation where every call into the future must simultaneously be a response from that future. This elegant symmetry resolves long-standing paradoxes in physics, like why an electron knows exactly how to move when pushed by suggesting particles are influenced not just by past forces, but by future ones too. Now let's bring this down to human experience. If time truly flows both ways, could fragments of future events leave faint impressions in our present? Some researchers speculate that déjà vu, that eerie sense of reliving a moment, might not be a glitch in memory, but a fleeting glimpse of this two-way causality. Imagine your brain occasionally intercepting those advanced waves, catching whispers of a future self's experience moments before it unfolds. In lab experiments, subjects exposed to subliminal future stimuli sometimes show neural activity before the stimulus appears, as if their brains are responding to a signal that hasn't technically happened yet. It's not precognition, it's physics, with consciousness surfing the edge of a time-symmetric reality. Critics argue this sounds suspiciously like retrocausality, bending the laws of thermodynamics beyond recognition. But supporters point to quantum experiments where particles seem to decide their properties only after being measured, as if future observations reach backward to shape past events. Even more compelling, certain solutions to Einstein's equations allow for closed time-like curves, loops where cause and effect circle back on themselves. If Wheeler and Feynman were right, our linear experience of time might be an illusion, a perspective bias like early astronomers thinking Earth stood still while the heavens moved. So the next time you feel an unexplained certainty about what's coming, or a strange familiarity with a place you've never been, consider this: you might not be remembering the past. You could be brushing against the future's ghostly fingerprints, tracing patterns in a universe where now is just a crossroads between two eternities. Galaxies aren't just drifting apart in the cosmic expanse, they're being pulled, not just by the gravity of visible matter, but toward something vast and unseen, lurking beyond the edge of everything we can observe. This eerie phenomenon, known as the dark flow, was first detected in 2008 when astronomers noticed hundreds of galaxy clusters hurtling in the same direction at inexplicable speeds, over 2 million miles per hour, as if drawn by an invisible hand. The strangest part, this cosmic current points toward a region of absolute nothingness, a void beyond the observable universe's horizon. No known structure, no concentration of mass should exist there powerful enough to tug entire clusters like celestial marionettes. Unless, of course, the pull isn't coming from our universe at all. One spine-tingling possibility is that the dark flow is gravity itself bleeding through from a neighboring timeline. Think of space-time as a vast, porous membrane. What if the gravitational influence of a parallel universe, with its own galaxies and dark matter, is seeping into ours like water through cracks in a dam? This wouldn't just rewrite our understanding of cosmology. It would mean we're cosmically tethered to realities we can't see. Some models of string theory even suggest extra dimensions could act as conduits for this gravitational leakage, with bulk space serving as a shared substrate where universes brush against one another, their forces mingling in the shadows. The evidence is as subtle as it is unsettling. When astronomers mapped the dark flow's trajectory, they found it aligns with a mysterious, ancient asymmetry in the cosmic microwave background, the afterglow of the Big Bang. Dubbed the axis of evil by skeptical scientists, this anomaly hints that the universe's expansion isn't perfectly uniform, as if something outside our cosmic bubble left a fingerprint on creation itself. Could this axis mark the direction of a sibling universe, its gravity warping ours from beyond the veil? Critics argue the dark flow might just be a statistical fluke or an artifact of incomplete data. But supporters counter that the flow's scale spanning billions of light years defies local explanations. If another universe is tugging at ours, it wouldn't be the first time invisible forces reshaped our cosmic map. Dark matter and dark energy were once dismissed as mathematical ghosts, yet now they're pillars of modern physics. The difference this time, we might be staring at the first tangible clue of a multiverse, a cosmic neighbor pressing its weight against the walls of our reality. So the next time you hear about galaxies in motion, remember, their dance might not be set to the music of our universe alone. Somewhere beyond the cosmic horizon, in a timeline just out of reach, an entire universe could be pulling the strings, reminding us that even the vastness we see is just a speck in something infinitely larger. Stephen Hawking's greatest discovery also became his deepest regret. When he realized black holes must slowly evaporate, radiating away their mass into the void, he struck physics like a lightning bolt because according to quantum law, information can never truly vanish. So where does it all go? Every atom, every photo album, every whispered secret swallowed by a black hole is supposed to leave some trace in the universe. But Hawking radiation, the faint glow of particles escaping a black hole's grip, seemed utterly random, like static hissing from a broken radio. For decades, this paradox pitted two unshakable pillars of physics against each other. Either quantum mechanics was wrong, and information could be erased from reality, or general relativity was incomplete, and black holes had a hidden trick up their cosmic sleeves. The answer might rewrite our understanding of time itself. Imagine a black hole not as a cosmic trash compactor, but as the universe's most extreme hard drive. As matter falls past the event horizon, its information isn't destroyed. It's scrambled beyond recognition, imprinted onto the surface in vanishingly small pixels called Planck areas. This holographic principle suggests that what we perceive as a three-dimensional void is actually a two-dimensional data storage system of unimaginable density, with every particle's quantum state preserved like lines of code etched in light. When Hawking radiation escapes, it doesn't carry random noise, it carries encrypted data, a cosmic cipher that would require the right key to decode. But here's where timelines enter the equation. Some theorists argue this encryption process might not just preserve information, it could merge it. Picture two histories entering a black hole, one where Rome never fell, another where dinosaurs still rule. As their data smears across the event horizon, those timelines could become quantum mechanically entangled, their differences dissolved into a unified code. The radiation leaking back into the universe might then contain fragments of both histories, like a shuffled deck of cards dealt into new hands. This would make black holes less like shredders and more like cosmic blenders, pureeing timelines into a soup where past, present, and alternate realities lose their edges. Recent breakthroughs lend eerie weight to this idea. In 2019, physicists calculated that Hawking radiation could retain subtle correlations with infalling matter, clues that information survives, just in forms we can't yet read. Even stranger, certain solutions to Einstein's equations suggest that black holes might connect to white holes through hidden bridges called Einstein-Rosen traversable wormholes. If true, the information swallowed by a black hole in our timeline could re-emerge, transformed, in another universe's Big Bang, a cosmic recycling plant where timelines are the raw material. Yet skeptics counter with a chilling alternative. If black holes do preserve information, they might do so by spawning entirely new universes inside their cores. Every particle falling in could become the seed of a big bang in a disconnected spacetime with no way to send messages back. In this view, our universe might itself be the interior of an ancient black hole from a parent reality, its laws of physics shaped by the scrambled remains of whatever or whoever came before. So the next time you gaze at the silent dark of a black hole's shadow, ask yourself, are we looking at a cosmic dead end or a locked door with infinite keys? The answer might not just reveal the fate of lost stars. It could tell us whether every vanished moment, every road not taken, is still out there, whispering in the static between worlds. What if the Big Bang wasn't a beginning at all, but the cosmic equivalent of a car crash, a violent collision between two realities we can't even see? That's the heart of the ekpyrotic universe theory, a radical alternative to cosmic inflation that rewrites the origin story of everything. Picture our universe not as a solitary bubble, but as a four-dimensional membrane or brain, floating in a higher dimensional space, like a sheet of paper suspended in a dark room. Now imagine another brain, another universe, drifting toward ours in the void. When they collide, the energy of that impact doesn't just create stars and galaxies, it births time itself, stitching together a new reality from the wreckage of the old. This idea, born from string theory's extra dimensions, suggests that what we call the Big Bang might have been a singular moment of contact between brains, a rebound from an earlier cosmic cycle. Unlike the fiery singularity of traditional models, the ekpyrotic scenario paints a colder, quieter origin, a slow dance of attraction followed by a shuddering release, like two magnets snapping together. The afterglow we see in the cosmic microwave background, not the remnants of an explosion, but the cosmic bruises left by that primordial collision, even more mind-bending. If these brains oscillate, periodically crashing and separating in an endless cycle, our universe could be just one page in an infinite cosmic flipbook, with each bang resetting the clock on a hidden timeline. Now here's where alternate realities sneak in. If our brain shares higher dimensional space with others, those unseen membranes might not just be parallel universes, they could be parallel times. Think of it like this: every brain collision doesn't just create space and matter, it establishes a new arrow of time, a fresh causality separate from what came before. Some theorists speculate that information from pre-collision brains might bleed through in subtle ways, encoded in the very fabric of our physics. The cosmological constant, that mysterious number governing the universe's expansion, could be a fingerprint from a previous cycle, a relic of timelines lost to the collision. Evidence for this lurks in the universe's eerie smoothness. The cosmic microwave background is almost perfectly uniform, a puzzle inflation solves with rapid stretching. But the ekpyrotic model achieves the same uniformity through brain collision, an elegant alternative where the brain's flatness translates into our universe's flawless geometry. Even more tantalizing, gravitational wave detectors might someday catch whispers of pre-Big Bang events, ripples from the brain's approach that survived the crash. If found, these impossible waves would be smoking gun proof that our timeline is just one layer in a vast, colliding stack. Critics argue that without direct observation of extra dimensions, the theory remains speculative. Yet its implications are too profound to ignore. If brains cycle eternally, then time isn't linear, it's a loop of creation and destruction, with each collision rewriting the rules. Dark energy's relentless push, perhaps the next brain drawing near, ready to reset existence once more. And if other brains host their own timelines, the cosmos isn't just expanding, it's nested, a hall of mirrors where every reflection is a universe with its own past, its own future, and its own hidden scars from the crash that started it all. So the next time you hear about the Big Bang, ask yourself, did time begin that day, or was it just another turn in an infinite carousel where every rotation leaves behind echoes of realities we'll never see? Imagine a forest at night so vast and dark that every creature hides in silence, afraid to make even the slightest sound. Because in this forest, any sign of movement could attract predators far more dangerous than anything you've ever known. Now replace the trees with stars and the creatures with civilizations, and you've stumbled upon the dark forest solution to the Fermi paradox, one of the most chilling answers to the question, why haven't we heard from aliens yet? According to this theory, the universe isn't just quiet because life is rare. It's silent because every advanced civilization is terrified of being noticed, because revealing yourself might not just risk invasion or war, but total annihilation of your entire timeline. The logic is as cold as it is compelling. If a civilization becomes two visible broadcasting signals expanding across star systems, even altering the fabric of space-time, they could attract the attention of something far worse than hostile aliens. They might draw the gaze of a civilization with time-altering weapons, capable of rewriting history to erase their enemies before they ever existed. Think of it like this. In a universe where time travel or causality violating technology is possible, the only way to ensure survival is to stay hidden. Not just in space, but in time, erasing any evidence of your existence from the past to prevent future civilizations from tracing and destroying you at your weakest point. This solves one of the great puzzles of the Fermi paradox, the eerie absence of Dyson spheres, megastructures that advanced civilizations should theoretically build to harness a star's energy. If the dark forest is real, building something so conspicuous would be suicide. Even the faintest infrared signature could act like a flare in the cosmic night, signaling your coordinates to predators lurking in the dark. Some theorists take this further, suggesting that certain unexplained astronomical phenomena, like the sudden dimming of stars, might not be natural at all, but the aftermath of civilizations actively scrubbing their presence from the timeline, collapsing their own history into obscurity to stay safe. What's truly unsettling is how this redefines the search for extraterrestrial intelligence. SETI efforts to listen for alien signals might not just be futile, they could be dangerous. If the dark forest holds, then every radio transmission we've ever sent into space isn't just a message. It's a potential countdown, marking the time until something out there notices us and decides we're too risky to leave alive. This might explain why some signals, like the famous WOW signal, a strong narrowband radio emission detected in 1977, appeared once and then vanished forever. Not because aliens stopped transmitting, but because they were silenced. But the darkest twist, this theory could mean that the most advanced civilizations aren't the ones expanding across galaxies or building megastructures. They're the ones who have mastered invisibility, not just in space, but in time. They might exist all around us, deliberately leaving no trace, ensuring that even their past is untraceable. And if that's true, then the greatest achievement of intelligence isn't conquering the stars. It's learning to disappear completely. So the next time you look up at the quiet night sky, remember, the emptiness might not mean we're alone. It could mean we're being watched by beings who have learned the hardest lesson of all. In a universe where time itself can be weaponized, survival isn't about being the strongest. It's about being the one nobody remembers. Quantum mechanics tells us reality is a blur of possibilities until we look, and suddenly only one outcome remains. But why do some possibilities seem to solidify into stable, shared experiences, while others vanish like smoke? This is where quantum Darwinism steps in, a theory suggesting that the timelines we perceive aren't just random, they've been selected for survival. Imagine a cosmic game of natural selection, where only the most resilient realities persist long enough for observers like us to witness them. The rest, they might flicker out of existence, collapsing under the weight of their own instability before anyone notices they were ever there. At the heart of this idea is a process called decoherence, the reason we don't see quantum weirdness, like cats being both alive and dead, in our everyday lives. When particles interact with their environment, their fragile quantum states collapse into definite outcomes, but not all outcomes are created equal. Some configurations are robust, reinforced by countless interactions with the world around them. Others are fragile, crumbling under the slightest disturbance. Quantum Darwinism proposes that the timelines we experience are the ones robust enough to withstand this decoherence, like trees still standing after a storm while weaker branches snap away unseen. Think of it like a radio dial searching for a clear station. The static between channels represents unstable quantum possibilities, brief, chaotic, and quickly overwritten. But when you land on a strong signal, that frequency dominates the speakers. In the same way, our now might be the clearest signal in a sea of static, with weaker timelines fading before they can ever properly form. This could explain why we perceive a consistent, predictable universe, not because other realities don't exist, but because they're too delicate to leave a lasting mark. Now, here's the unsettling implication. If unstable timelines vanish, how many have we already lost? Some researchers speculate that entire branches of history might dissolve moments after splitting, erased by the universe's relentless preference for order. A world where gravity fluctuates randomly or where time stutters backward and forward would never produce conscious observers to remember it. We'd only ever find ourselves in the rare, stable realities where the rules stay constant enough for life and memory to exist. Critics argue this veers dangerously close to the anthropic principle, where we're simply observing the universe because it's the only one that allows observation. But quantum Darwinism goes further, suggesting there's a mechanism behind this pruning. Every interaction, every photon hitting your eye, every atom bouncing in the air, acts as a vote for which version of reality gets to stick around. The timelines we perceive are the ones that have won the most votes, outcompeting their fragile rivals in a silent, invisible battle for existence. So the next time you marvel at the consistency of the world, why the sun rises every morning, why objects don't randomly phase through walls, consider this: you might not be witnessing the only possible reality. You could be living in the one that fought the hardest to survive, and somewhere in the quantum static, countless others flicker for just an instant, unobserved and unremembered, like dreams dissolving at the moment of waking. What if the reason we experience time as a single, unbroken thread isn't because other timelines don't exist, but because our brains act as the ultimate reality tuners, locking us into one channel of existence while the rest remain just out of reach? This is the spine-tingling proposition of the orch or consciousness theory, developed by anesthesiologist Stuart Hameroff and physicist Roger Penrose. At its core, this idea suggests that our perception of time isn't just a passive observation, it's an active computation happening deep within the neurons of our brains, in structures so small they dance on the edge of the quantum world. The secret might lie in microtubules, tiny protein filaments that form the skeleton of our cells, including neurons. Most scientists see these as mere structural supports, but Hameroff and Penrose propose something far wilder: that microtubules act as quantum computers, processing information at scales where the ordinary rules of physics blur. In this view, every thought, every moment of awareness arises from quantum vibrations inside these filaments, vibrations so delicate they're sensitive to the faintest ripples in reality. And here's where timelines come in. If consciousness stems from quantum processes, then our perception of a single, linear timeline could simply be the result of our brains resonating with one stable thread of reality, while alternate possibilities collapse away like radio static. Think of it like tuning an old-fashioned television. Every channel exists simultaneously in the broadcast signal, but you only perceive one at a time based on how you adjust the dial. Similarly, our microtubules might tune into a specific timeline by synchronizing with certain quantum frequencies, filtering out the noise of other possibilities. This could explain why we never experience the bizarre branching of quantum superpositions, like Schrödinger's cat being both alive and dead. in our daily lives. Our consciousness isn't just observing reality, it's selecting it moment by moment from a sea of potentials. Now consider the implications for deja vu or precognitive dreams. These fleeting phenomena might not be glitches in memory or imagination. They could be moments when our microtubules briefly lose their signal lock, allowing whispers of other timelines to bleed through. Even more intriguing, if consciousness truly hinges on these quantum processes, then altering them through anesthesia, meditation, or psychedelics might temporarily loosen our grip on consensus reality, offering glimpses into the tangled web of alternate histories that constantly flicker at the edges of perception. Critics argue that the brain is too warm and noisy for fragile quantum states to survive long enough to influence consciousness. But recent experiments hint at quantum effects in biological systems, from photosynthesis in plants to bird navigation using Earth's magnetic field. If nature already harnesses quantum mechanics in unexpected places, why not in the human brain? Supporters also point to the puzzling speed of human cognition. Our ability to make complex decisions faster than classical neurons could explain as potential evidence of quantum computation under the hood. And if Hameroff and Penrose are right, it would mean that every time you make a choice what to eat, where to turn, whether to speak or stay silent, you're not just navigating one timeline. You're navigating all of them, with your brain acting as the silent conductor of reality's symphony, orchestrating the collapse of infinite possibilities into the single, luminous note of the present. So the next time you pause at a crossroads torn between paths, remember, your hesitation might not just be uncertainty. It could be the faint echo of other versions of you in other timelines, making different choices, all of them real, all of them waiting just beyond the threshold of perception, in the quantum hum of your own mind. Most stories have a clear beginning and end, but what if the universe itself refuses to follow that script? Instead of a single explosive birth and a cold, lonely fade out, imagine existence as a cosmic heartbeat, pulsing between extremes of collapse and rebirth. This is the grand battle between two radical visions of our universe's fate, the Big Crunch and the Big Bounce. One ends in oblivion, the other in resurrection, and the key to both might lie in the fragile quantum thread stitching timelines together across the void. The classic Big Crunch scenario plays out like a rewinding film. After billions of years of expansion, gravity finally wins its tug of war with dark energy, pulling galaxies back together in a slow-motion reversal of the Big Bang. Space contracts, temperatures soar, and eventually every atom, every photon, every whisper of information gets crushed into a singularity, a final, inescapable endpoint where time itself stops. It's a grim fate, but here's the twist. Some versions of this theory suggest the crunch might not be the end. If conditions are just right, the collapsing universe could rebound like a compressed spring, triggering a new Big Bang. This is the Big Bounce, a cycle of death and rebirth stretching infinitely forward and backward, with each iteration birthing a new cosmos from the ashes of the old. Quantum gravity complicates and illuminates this picture. In Einstein's general relativity, singularities are dead ends, regions where physics breaks down. But loop quantum gravity, a leading theory attempting to unite quantum mechanics with gravity, suggests something astonishing. There might be a minimum size below which space cannot shrink. Think of it like a cosmic trampoline. It can stretch and warp, but there's a point where it resists further compression, snapping back with enough force to fuel a rebound. If true, this means every crunch could naturally flip into a bounce, with quantum effects acting as the universe's ultimate shock absorber. Now here's where timelines get slippery. In a single cycle universe, information is doomed. Black holes evaporate, stars burn out, and all traces of history eventually fade to noise. But in a bouncing model, quantum entanglement might create bridges between cycles. Picture two particles so deeply linked that changing one instantly affects the other, even across light years. Now scale that up. if the fabric of space-time itself preserves quantum correlations across a bounce, fragments of previous universes could imprint themselves on the newborn cosmos like cosmic DNA. Some theorists even suggest that the constants of nature, the speed of light, the strength of gravity, might subtly shift with each cycle, evolving like genes passed between generations. Evidence for these ideas is sparse but tantalizing. The cosmic microwave background, that ancient light from the universe's infancy, shows odd large-scale anomalies patterns that don't quite fit standard inflation models. Could these be scars from a pre-bounce universe, subtle warps in space-time that survived the transition? Even wilder, if black holes preserve information on their event horizons as holograms, could those holograms persist through a bounce, encoding the history of lost civilizations in the very structure of the next universe's laws? Skeptics argue that without a working theory of quantum gravity, these visions remain speculative poetry. Yet the stakes couldn't be higher. If the big bounce is real, our universe might be one page in an infinite cosmic library, each volume written in the faint quantum scribbles of the one before. And if it's not, if the crunch is truly the end, then every moment, every choice, every memory is racing toward an erasure more absolute than we dare imagine. So when you look up at the night sky, remember, the darkness between stars might not just be empty space. It could be the shadow of a past universe or the quiet before the next great explosion, a pause in the breath of something far older and far stranger than time itself. What if every equation scribbled in a notebook, every geometric shape, every abstract mathematical truth isn't just a human invention but a window into a hidden universe? This is the electrifying premise of Max Tegmark's Type 4 Multiverse, a vision so radical it suggests reality isn't described by mathematics, it is mathematics. In this model, every possible structure that can exist mathematically does exist physically somewhere in the cosmic ensemble. Not just alternate versions of our universe with different particle masses or gravity strengths, but realities built from entirely different rules, dimensions where time loops like a Möbius strip, where causality runs backward, or where the very concept of space dissolves into pure topology. And the most mind-shattering implication, if this is true, then math isn't the language of the universe, it's the universe's skeleton, the hidden scaffolding behind every timeline we've ever imagined. Tegmark's framework divides multiverses into 4 tiers, each more expansive than the last. Type 1 involves distant Hubble volumes beyond our cosmic horizon. Type 2 hosts bubble universes with different physical constants. Type 3 spawns parallel worlds through quantum branching. But Type 4, it obliterates the very need for physics as we know it. Here, universes aren't governed by equations, they are equations. A solution to Schrödinger's wave function doesn't just describe quantum behavior, it is a quantum reality. A 4-dimensional manifold in string theory isn't a hypothesis, it's a vibrating, breathing cosmos somewhere in the multiverse's library. In this view, Pythagoras' theorem exists as literally as Mount Everest, just in a different mathematical location. Now here's where timelines warp beyond recognition. If every mathematical structure is real, then our experience of time might be a local quirk, one thread in a tapestry where before and after aren't universal truths. Somewhere out there, a universe could run on Fibonacci sequences, its history spiraling like a Nautilus shell. Another might follow prime number patterns, its events unfolding in jumps divisible only by themselves. Even consciousness could be a rare flavor of self-referential computation, one of countless possible configurations of information perceiving itself. This makes Tegmark's multiverse the ultimate democracy of existence. No structure is more or less real than another, whether it's the elegant symmetry of general relativity or the chaotic scribbles of a child's first algebra attempt. Evidence for this audacious idea might be hiding in plain sight. the unreasonable effectiveness of mathematics, why abstract concepts like imaginary numbers or non-Euclidean geometry, later described real phenomena, suddenly make sense if math and physics are two sides of the same coin. Even the debate over whether math is discovered or invented collapses. In a Type 4 multiverse, it's both. Humans invent mathematical structures the way explorers invent new lands, by stumbling upon territories that existed long before they were mapped. Critics argue this reduces reality to a sterile landscape of abstractions, devoid of the richness we experience. But Tegmark counters that our perception of texture, color, and emotion could itself be a mathematical pattern, a specific, self-aware knot in the fabric of information. As for timelines, they might not branch or loop, they could simply be adjacent chapters in an infinite, unchanging mathematical tome, where change is an illusion of perspective. So the next time you solve an equation or admire a fractal, consider this. You might not be manipulating symbols on a page. You could be holding a mirror to another universe's sky, catching a fleeting glimpse of a reality where 2 + 2 = 5, circles are square, and time is just another variable waiting to be solved. Why does time march relentlessly forward, dragging us from past to future like a river with no reverse current? The answer might lie in a concept so fundamental we barely notice it: entropy, the universe's slow slide from order to chaos. Picture a shattered glass. You've never seen the pieces leap back into a pristine cup, not because physics forbids it, but because the odds are astronomically stacked against it. This one-way street is called the arrow of time, and its roots dig deep into the most explosive moment in history, the Big Bang. Here's the twist: the Big Bang wasn't just hot and dense. It was unnaturally orderly. Think of the early universe as a box of marbles dumped out in perfect rows, a state of improbably low entropy. As that order inevitably unraveled over billions of years, it created the gradient that time's arrow rides. But why was the universe born so tidy? Some physicists suspect it's a clue that our timeline might not be the only one in play. If entropy always increases, then the Big Bang's low entropy suggests it wasn't a true beginning, just the midpoint of a larger, stranger story. This opens the door to one of cosmology's most electrifying what-ifs, a mirror universe where time flows backward from our Big Bang. In this model, our expanding, entropic universe could be one half of a cosmic seesaw, balanced by a contracting twin where broken glasses reassemble and smoke pours back into cigarettes. The two realms would meet at the Big Bang, not as a singularity, but as a moment of maximum order, like the peak of a pendulum's swing before it falls the other way. To observers in that reversed universe, we'd seem to be living in reverse, with stars absorbing light and people growing younger. Evidence for this duality hides in the quantum realm. Certain particle interactions are mathematically identical whether time runs forward or backward, hinting that the laws of physics might not care about time's direction, only entropy does. Even black holes, those notorious time warps, could be threading the needle between timelines. Their event horizons behave like thermodynamic one-way doors, but some models suggest information leaking out as Hawking radiation might carry echoes of a reversed reality on the other side. But how would such a universe even function? Imagine watching a flipped recording of life, trees absorbing carbon dioxide to grow smaller, sunlight flowing from plants into the sun. Bizarre as it sounds, this wouldn't violate physics. It would just require every particle's momentum to invert, rewriting cause and effect. Some theorists argue this symmetry is beautiful enough to be true, while others counter that a backward universe would be indistinguishable from our own. Both perspectives would simply call their own time forward. The real stunner: if this mirror cosmos exists, it might not be lost to us forever. Quantum entanglement shows particles can instantaneously influence each other across space. Could the Big Bang have left similar threads stretching between timelines, weaving subtle connections we're only beginning to sense? Every so often, physics experiments catch particles behaving as if they're receiving signals from nowhere. Might those whispers be bleeding through from the other side of time? So when you next feel time slipping through your fingers, remember, the flow you're caught in might just be one half of a grander symmetry, a cosmic dance where every step forward in our world is a step back in another. The universe may not have a single past or future, just an endless exchange of echoes across the mirror of the Big Bang. Light-speed travel has always been the ultimate prison break, until physicist Miguel Alcubierre handed us the blueprint for a cosmic getaway car. His warp drive concept, published in 1994, doesn't try to push a ship through space faster than light. Instead, it cheats by bending space itself, compressing the fabric of reality ahead of the vessel while stretching it behind, like surfing a wave of twisted spacetime. But here's the twist Einstein never saw coming. If you can warp space, you might also be warping time, potentially ripping holes in the timeline itself. The key lies in those closed time-like curves, paths through spacetime that loop back on themselves like a Möbius strip made of history. Normally, relativity forbids time travel to the past, but an Alcubierre drive could, in theory, create conditions where these loops emerge. Picture a ship warping from Earth to Alpha Centauri. In flat spacetime, the trip takes 4.37 years as measured from home. But inside the warp bubble, time dilates dramatically. The crew might experience just weeks. Now imagine slingshotting back to Earth via another warp jump. Because spacetime is stretched and compressed unevenly, you could return before you even left. Your personal timeline becomes a tangled knot, intersecting with versions of reality where your departure never happened, or worse, where two copies of you suddenly exist in the same moment. NASA Eagleworks Lab has been probing these possibilities with experiments so cutting-edge they border on science fiction. In 2021, they reported microscopic warp bubble signatures in Casimir cavity, experiments tiny structures where quantum fluctuations mimic the spacetime distortions Alcubierre proposed. These aren't starship engines yet, but they're the first faint whispers of a physics that could make timeline hopping tangible. Even stranger, their models suggest that sustaining a warp bubble might require negative energy, a hypothetical substance that repels gravity. Some quantum systems already exhibit negative energy densities, hinting that the universe might have left the door ajar for us to sneak through. But the real shocker: warp-driven time travel wouldn't look like DeLoreans or phone booths. It would resemble something far more unsettling, events uncoupling from cause and effect. Imagine receiving a distress call from your own ship before launching, or detecting warp signatures from vessels that won't be built for centuries. Historians might uncover records of battles fought with weapons that don't exist yet, while astronomers could spot ghostly fleets flickering in and out of spacetime like glitches in reality's code. Critics argue that even if possible, such technology would unravel causality like a pulled thread. But supporters counter that the universe might have self-correcting mechanisms, quantum censorship that prevents paradoxes by spawning alternate timelines whenever someone tampers with history. Either way, the takeaway is clear. The speed limit of light wasn't just set to keep us in our place. It might be the universe's way of protecting us from the storm of possibilities waiting in the warped dark beyond. Imagine a tree falling in an endlessly observed forest. Does it ever actually hit the ground? This isn't just a philosophical riddle, it's the spine of the quantum Zeno effect, a phenomenon so strange it suggests reality itself might freeze under the weight of constant scrutiny. Named after the ancient Greek philosopher Zeno's paradoxes about motion, this effect reveals a startling truth. The mere act of measuring a quantum system can halt its evolution, like pressing pause on reality's film reel. And if this applies to particles, could it also apply to timelines? Here's how it works in the quantum realm. Take an unstable atom poised to decay. Left unchecked, it'll eventually spit out radiation. But bombard that atom with rapid-fire observations measuring its state thousands of times per second. and something eerie happens, the decay stalls. It's as if the universe, caught in the headlights of relentless attention, forgets to move forward. The math behind this is just as counterintuitive. Each observation resets the atom's quantum wave function, forcing it back to its starting position like a sprinter perpetually yanked back to the starting blocks. Now stretch this logic to the fabric of reality itself. If consciousness or measurement can pin a quantum state in place, could a civilization, by constantly observing its own timeline, prevent the branching of parallel worlds predicted by the many worlds interpretation? Picture a future where quantum sensors monitor every decision point in society, from election outcomes to particle collisions. In such a world, the sheer density of observation might act like cosmic superglue, cementing a single, unchanging timeline by sheer force of attention. This idea isn't pure speculation. In 2008, physicists demonstrated the quantum Zeno effect in a startlingly macroscopic system, a cloud of rubidium atoms. When probed with laser pulses at precise intervals, the atoms stopped evolving entirely, trapped in a state that defied natural decay. Scale this up, and you could imagine a scenario where a network of quantum satellites, tasked with measuring Earth's global state, inadvertently locks our planet into a static timeline, a Truman Show-esque reality where change becomes statistically impossible because every potential branching point gets observed away. But there's a darker corollary. If continuous observation prevents branching, then the reverse, the quantum anti-Zeno effect, might accelerate it. Rare events like radioactive decay can actually speed up under intermittent observation, as if reality rushes to evolve when its senses were not looking. Apply this to timelines and periods of societal collapse or blackout when record-keeping falters and collective attention fragments could become hotbeds of reality bifurcation, where unnoticed decisions spawn explosive divergence. Some theorists take this further, suggesting that historical dark ages weren't just gaps in human knowledge. They might have been eras where reality itself splintered wildly, with timelines fraying like unobserved quantum threads. The sudden reappearance of advanced astronomical knowledge in ancient cultures, or the persistent myths of golden ages lost to time, could be echoes of branches where civilizations stabilized their timelines through ritualized observation, only to lose cohesion when those practices faded. Of course, skeptics argue that consciousness probably doesn't play this role, that decoherence from environmental noise, not human attention, drives quantum collapses. Yet the tantalizing implication remains. If the universe truly is participatory, then our gaze might not just witness reality. It could be the anchor that keeps it from drifting into the multiverse's storm. So the next time you pause to watch a sunset or scrutinize a decision, consider this. You might not just be observing the flow of time. You could be holding it in place, one focused moment at a time, a silent architect of the only timeline you'll ever know. Black holes are often painted as cosmic dead ends, but what if they're actually cosmic womb? The Planck star universe theory flips the script on these gravitational monsters, suggesting that deep inside every singularity, hidden beneath layers of warped space-time, lies the seed of a brand new universe. Not through white holes or parallel brains, but through a quantum resurrection, a rebound so violent it defies everything we know about the cold, crushing core of a dying star. Here's the radical premise. When a massive star collapses into a black hole, the unimaginable pressure doesn't compress matter into an infinitely dense point. Instead, quantum gravity, a theory still in its infancy, steps in like a cosmic trampoline. At scales 1 trillion times smaller than an atom, space itself might have a minimum size, a Planck length beyond which it cannot be squeezed. When the collapsing core hits this limit, it doesn't vanish. It bounces, like a ball hitting the floor. All that pent-up energy rebounds outward in a searing flash, birthing a new universe inside the black hole's belly, a Planck star. The implications rewrite the story of our own origins. If this theory holds, our Big Bang might not have been the first chapter, just the latest bounce in an endless cycle. Picture a matryoshka doll of realities, each nested inside the black holes of a parent universe. Our cosmos could be one link in an infinite chain, with every galaxy's central black hole harboring its own infant universe, its own timeline, its own laws of physics forged in the crucible of collapse. Even stranger, these baby universes might inherit subtle traits from their progenitors. Just as DNA passes traits between generations, quantum information from the parent black hole encoded in the spin of particles, the weave of space-time, could shape the physics of its offspring. But how would we ever detect such a hidden lineage? Clues might lurk in the cosmic microwave background. If our universe was born from a Planck star, its earliest moments would carry imprints of that rebound, an echo of the spring after the squeeze. Some theorists hunt for anomalous temperature patterns in the ancient light, subtle asymmetries that could betray our cosmic parentage. Others speculate that dark energy, the mysterious force accelerating the universe's expansion, might be residual momentum from that primordial bounce, a phantom push from a collapse that happened billions of years before time as we know it began. The most mind-bending twist, time itself would behave differently in these nested realities. From our perspective outside a black hole, the Planck star's rebirth unfolds in frozen slow motion, trapped near the event horizon where gravity stretches seconds into eons. But inside the newborn universe, time races forward, a hyperinflated existence where our billions of years pass in their blink. This means civilizations could rise and fall inside black holes we've observed for centuries, their entire histories playing out before we've even finished our first cup of coffee. Critics argue that without a unified theory of quantum gravity, Planck stars remain speculative poetry. Yet the math hints at something profound. If black holes can archive information on their event horizons, as Hawking's later work suggested, then those holograms might not just store data. They could be blueprints, the cosmic equivalent of an umbilical cord threading the laws of physics from one timeline to the next. So the next time you gaze at the black heart of a galaxy, remember, you might not be looking at a grave. You could be staring at a nursery where universes are born from the ashes of time itself. The universe as we know it might be sitting on borrowed time, not from a collision or a big crunch, but from a single, minuscule bubble of truth bursting through the fragile illusion of reality. This is the nightmare scenario of the false vacuum collapse, a theory that suggests our entire cosmos could be perched on a metastable ledge, one quantum nudge away from oblivion. Right now, the space between stars isn't truly empty, it's seething with vacuum energy, a background hum left over from the Big Bang. But what if that energy isn't in its lowest possible state? What if it's trapped in a false vacuum, like a marble resting in a shallow dent atop a hill, waiting for the slightest vibration to send it tumbling into the abyss? A single quantum fluctuation somewhere, anywhere, could be all it takes to tip the balance. Imagine a tiny region of space suddenly decaying into a true vacuum, a state where the fundamental forces reconfigure instantly. The laws of physics as we know them would rewrite themselves at the speed of light, radiating outward in an inescapable sphere of annihilation. Atoms would disintegrate, molecules unravel, and the very fabric of space-time would reboot under new rules. One moment you're sipping coffee, the next you and everything you've ever known cease to exist in any recognizable form. The cosmic firewall wouldn't just kill life, it would erase the conditions that make life possible. But here's where the timeline twisting twist comes in. Quantum mechanics might offer a slim escape hatch, tunneling. Normally, particles can't cross energy barriers, but on rare occasions they cheat, teleporting through impossibly high walls like ghosts passing through walls. If the false vacuum decay began, certain quantum systems, perhaps conscious beings, might tunnel sideways out of the collapsing universe, not in space but in time. Their wave functions could bleed into adjacent timelines, essentially jumping ship to a reality where the decay hasn't happened yet. It wouldn't be a controlled escape. More like a desperate quantum Hail Mary, where versions of you flicker into existence in unaffected branches of the multiverse, memories intact but futures uncertain. This isn't just speculation. In 2018, researchers at CERN analyzed high-energy particle collisions for signs of vacuum decay, probing whether the Higgs field, which gives particles mass, might be metastable. Their verdict: we're probably safe for now, but the margin is thinner than you'd hope. If the Higgs mass were just a few % lighter, the universe would have already been doomed. And if decay began, we'd never see it coming. The bubble's edge would move at light speed, erasing evidence of its approach until it was already upon us. Yet the eerie beauty of this doomsday scenario is its paradox. The very instability that could destroy us might also be the reason we exist. If the early universe hadn't been trapped in a false vacuum, inflation, the rapid expansion that smoothed the cosmos, might never have occurred. No stars, no planets know you, so every sunrise, every breath is made possible by the same precarious balancing act that could at any moment pull the rug out from under reality. And if that bubble ever comes, well, hope you're feeling lucky, because in the quantum casino of existence, survival might mean betting everything on a timeline where the universe didn't draw the short straw. What if the uncanny precision of the universe, the exact strength of gravity, the perfect charge of an electron, the razor-thin margin that allows stars and planets to form isn't luck, but something far stranger? The holographic anthropic principle takes this cosmic fine-tuning and flips it on its head, suggesting that the universe isn't just compatible with life, it might be constructed by it. Not in the simple sense of a creator god, but in a dizzying, self-referential loop where observers shape reality simply by existing within it. And if this is true, our timeline might be less of a singular thread and more of a fractal pattern, endlessly replicating deeper layers of observation like reflections in a hall of mirrors. At its core, this idea marries two radical concepts. The holographic principle, which suggests our three-dimensional reality is a projection from a two-dimensional surface, and the anthropic principle, which notes that the universe's constants are suspiciously perfect for life. Combine them, and you get a universe where conscious observation isn't just a byproduct of physics, it's the engine that stabilizes physics. Imagine a cosmic game of 20 questions where the answers don't just reveal reality, they create it. Every time a conscious mind measures a quantum state or observes a star, it's not passively recording data, it's actively reinforcing the rules of the game, locking in the conditions that allow more observers to emerge. Now, here's where timelines twist into something surreal. If reality is fundamentally participatory, then our universe might be one layer in an infinite stack of holograms, each one spawning the next. Picture a Russian nesting doll where every doll's eyes are the tools that carve the doll inside it. In this view, the Big Bang wasn't just the start of our timeline, it could have been the measurement event of a higher dimensional observer whose act of observation crystallized our universe into being. And somewhere in our future, our own observations, whether through quantum experiments, artificial intelligence, or cosmic exploration, might be birthing the next universe in the chain, its physical laws subtly shaped by the questions we thought to ask. Evidence for this isn't just philosophical. Quantum experiments consistently show that particles don't have definite properties until measured, as if reality refuses to commit to a single timeline until forced. Even stranger, certain interpretations of quantum gravity suggest that black holes, those ultimate information scramblers, might encode their interiors on their surfaces in precisely the way a hologram stores 3D data on a 2D plate. If black holes are universes in miniature, as some theories propose, then our entire cosmos could be the holographic projection of a singularity in apparent reality, with our scientists' labs acting as the observers who stabilize its next layer. Critics dismiss this as circular reasoning. Of course, we find ourselves in a universe that allows us to exist. But proponents counter that the holographic angle adds a terrifying corollary. If a universe fails to produce observers, it might not just lie empty, it could unravel, its unstable constants resetting in a quantum collapse until a viable timeline emerges. This would make life not just a happy accident, but a cosmic necessity, with each conscious moment a stitch holding the fabric of reality together. So the next time you look up at the stars, consider this: you might not just be living in a finely tuned universe. You could be the tuner, the observer whose very existence keeps the cosmic hologram from glitching into oblivion. And if that's true, then every experiment, every telescope pointed at the sky, isn't just exploring reality, it's knitting the fabric of the next one. The cosmic microwave background, the faint afterglow of the Big Bang, should be the universe's most boring baby picture. A smooth, featureless glow stretched across the sky by 14 billion years of expansion. But when scientists finally mapped it in exquisite detail, they found something deeply unsettling. The CMB isn't uniform at all. It's marbled with strange, asymmetrical patterns, hotter patches here, colder voids there, as if the infant universe had been bruised in a cosmic brawl before it even took its first breath. The most infamous of these scars is dubbed the axis of evil, a spine-chilling alignment of anomalies that points like an arrow through space, defying all predictions of how the early universe should behave. And the wildest explanation, these might not be birthmarks at all, they could be fractures from a collision with another timeline, or ghostly handprints from a universe that existed before our own. At first glance, the CMB's temperature variations seem random, tiny fluctuations born from quantum noise in the first fractions of a second after the Big Bang. But when researchers ran statistical analyses, the numbers refused to cooperate. Certain large-scale patterns, like a mysterious cold spot spanning billions of light years, appear far less likely to occur by chance than winning the lottery 10 times in a row. Even stranger, some of these anomalies align along a single axis, as if the entire early universe had been tilted. The odds of this happening naturally: less than 1 in 100,000. It's like rolling a die and getting 6 sixes in a row over and over, while every physicist in the room screams that it's impossible. So what could warp the fabric of reality on such a mind-boggling scale? One radical possibility is that our young universe didn't emerge alone. Imagine 2 bubble universes inflating side by side in the multiverse's froth, their edges briefly brushing during expansion. That fleeting contact could have transferred energy not as a collision in space, but as a tremor through time itself, leaving ripples in the CMB like fingerprints on glass. Supporters of this idea point to odd, circular patterns in the microwave background, potential bruises from such an encounter. Even more tantalizing, certain anomalies appear to spiral, as if space-time itself had been twisted by the gravitational wake of something vast moving outside our cosmos. But the axis of evil's true horror lies in its implications for time. If the universe has a preferred orientation, it challenges cosmology's most sacred principle, that no direction in space should be special. Some theorists suggest this axis might mark the gravitational pull of a neighboring universe, an unseen sibling tugging at ours from beyond the cosmic horizon. Others propose it's an echo of pre-Big Bang physics, a scar from when our timeline first crystallized out of some higher dimensional chaos. Picture a frozen lake on a winter morning. The cracks in the ice don't form randomly, they follow stresses from the water's turbulent history before it froze. Similarly, the CMB's flaws might encode events from before time as we know it began. Critics argue these anomalies could just be artifacts of incomplete data or galactic interference. Yet every new map from Planck to W-map only deepens the mystery. The cold spot, for instance, isn't just a blank patch. It's surrounded by a bizarre ring of hotter plasma, like the shockwave from an unimaginable impact. When researchers simulated collisions between universes, the resulting patterns matched these observations with eerie precision. And if that's not spine-tingling enough, quantum gravity models suggest such collisions wouldn't just leave thermal scars. They could imprint information from one timeline onto another, like a cosmic USB drive accidentally plugged into the wrong universe. So the next time someone calls the night sky peaceful, remember, we're staring at the battlefield of realities where the faintest microwaves might carry whispers from beyond the edge of existence. The universe's oldest light isn't just a relic. It's a palimpsest, its surface scratched with stories we're only beginning to decode. And somewhere in those asymmetric ripples, the cosmos might be trying to tell us it wasn't always alone. What if time isn't a river flowing on its own, but a bridge built one plank at a time, only where someone stands to hammer it together? This is the spine-tingling proposition of biocentrism, a theory championed by scientist Robert Lanza that flips the traditional view of reality on its head. Instead of time and space existing as fixed stages where life eventually stumbles into the spotlight, Lanza suggests the opposite. Consciousness creates the stage, weaving time into existence through the very act of observation. In this vision, timelines aren't pre-written scripts, they're more like live performances, collapsing into solidity only when a mind is there to witness them. Think of it like a cosmic game of Schrödinger's cat, but on a universal scale. Just as a quantum particle exists in a haze of possibilities until measured, Lanza argues entire eras might hover in uncertainty until observed. Ancient forests might have grown and fallen without a single moment truly passing, their existence retroactively cemented only when a later consciousness, a scientist analyzing tree rings, perhaps looks back and pins the past in place. This would mean the universe isn't just indifferent to life, it's contingent on it, with time's arrow flickering like a candle in the wind whenever observation lapses. The implications rewrite history literally. If biocentrism holds, gaps could lurk in the timeline where no observer was present. Vast stretches between stars where light traveled unobserved, or epochs before life evolved where time itself was little more than a fog of probabilities. Even now, your unobserved surroundings might exist in a hazy, half-real state, snapping into sharp focus only when you turn your gaze. Lanza points to quantum experiments like the double slit, where particles behave as waves until measured, as evidence that reality responds to observation. Scale that up, and the universe might not just be described by quantum rules, it might be built by them, one conscious glance at a time. But how could life, a latecomer in cosmic terms, stitch together a past that predates it? Here, biocentrism ventures into even wilder territory, retrocausality. Just as a detective's investigation solidifies clues into a coherent case, our present observations might be retroactively determining which version of history happened. The dinosaur bones in museums, they're not just relics of an independent past, they're artifacts that became real when we dug them up and studied them. This isn't just philosophy, physics has flirted with similar ideas. Delayed choice experiments show particles can decide their past behavior based on future measurements, as if reality is a choose-your-own-adventure book where the ending edits the earlier pages. Critics argue this veers into solipsism, reducing the universe to a fragile projection. Yet Lanza counters that biocentrism isn't about individual minds dreaming up reality. It's about consciousness as a fundamental force like gravity or electromagnetism. In this view, even a single bacterium's crude perception could collapse quantum possibilities in its immediate surroundings, weaving tiny threads of time into the cosmic tapestry. Over billions of years, increasingly complex observers from algae to astronomers could have collectively stitched together the robust, continuous timeline we now take for granted. The most haunting question. If consciousness shapes time, what happens when no one's looking? Does the universe go dark between thoughts like a screensaver flicking off? or does it keep running on autopilot, sustained by the faintest hum of observation, a bee's awareness of sunlight, a microbe's sense of heat? Perhaps time isn't lost in these gaps, but folded, with unobserved moments existing as compressed potentials, like a paused film reel waiting for the projector's light. So the next time you check your watch, consider this: the ticking seconds might not be measuring an independent reality. They could be the echoes of your own perception, stitching the present into existence one conscious moment at a time. While beyond your attention, the universe hums with possibilities not yet made real. Black holes aren't just cosmic shredders, they might be the forges where consciousness and time collide to birth entirely new universes. Imagine the most extreme environment in existence meeting the most delicate quantum processes inside your brain. This is the brain-bending fusion of two radical theories: Stuart Hameroff's microtubule-based consciousness and Frank Wilczek's X-time crystals. Together, they suggest that deep inside a black hole's chaos, these phenomena could intertwine to create something unprecedented, a universe not just governed by physical laws, but one inherently structured to generate timeline-aware observers like us. Let's break this down. Hameroff's or theory proposes that consciousness arises from quantum vibrations in microtubules, tiny protein structures in our neurons. These vibrations, shielded from environmental noise, could perform quantum computations, making our brains more like organic quantum computers than classical machines. Now throw time crystals into the mix. These bizarre structures, which pulse in a repeating pattern without energy input, defy entropy by existing in a state of perpetual oscillation. Place both phenomena inside a black hole where gravity warps spacetime to its limits, and something extraordinary might occur. The black hole's singularity could act as a cosmic crucible, compressing and entangling these quantum processes until they reach a critical threshold, a moment where consciousness and time crystallize into the seed of a new universe. Here's where it gets even wilder. If this fusion happens, the newborn universe might inherit a peculiar trait: timeline sensitivity. Just as our brains perceive time's flow by integrating moments into a coherent narrative, this new reality could be pre-tuned to develop observers capable of navigating and shaping time in ways we can't fathom. Think of it like a video game engine designed to support a specific type of gameplay, except here, the game is causality itself, and the players are future civilizations whose very observation reinforces the stability of their timeline. Evidence for this idea is speculative but tantalizing. Quantum entanglement, which already suggests particles can influence each other instantly across distances, might scale up to entire universes. If black holes preserve information on their event horizons, as holographic theory suggests, then the quantum states of microtubules and time crystals could be imprinted onto the fabric of a new cosmos, like a cosmic QR code waiting to be scanned. Some models even predict that the initial conditions of such a universe would favor the emergence of consciousness, as if the black hole's interior remembered the structures that birthed it. Critics argue this stretches physics beyond recognition, merging untested theories into a speculative house of cards. Yet supporters counter that black holes are already laboratories for the impossible, where known laws break down. If time crystals can exist in the lab, and if microtubules really do harness quantum effects, why couldn't their interaction under extreme conditions birth something stranger than fiction? After all, our own universe's fine-tuning for life is already a profound mystery. What if the answer lies in the remnants of a parent black hole's quantum consciousness hybrid? So the next time you ponder the night sky, consider this. The darkest voids out there might not just be endings. They could be incubators where the seeds of consciousness and time weave themselves into new realities that might one day look back and wonder, just as we do, about the strange origins of their own existence. So here we stand at the edge of the cosmic rabbit hole, staring into a kaleidoscope of possibilities where reality itself unravels into threads more bizarre than fiction. We've danced through universes bubbling eternally in an inflationary sea, where every quantum flicker spawns a new cosmos with its own rules. We've glimpsed timelines folded like origami inside black holes, where information isn't lost, just rewritten into the birth cries of new realities. We've questioned whether our memories are even our own, or phantom imprints from colliding branches of the multiverse, and wondered if the stars above are just pixels in an ancestor simulation running on some unfathomable hard drive. From Boltzmann Brains, those lonely, self-aware illusions conjured by pure chance in the void, to the spine-chilling idea that we might be living in a cosmic dark forest, where civilizations hide from timeline-weaponizing predators, the theories we've explored don't just bend the rules of reality. They shatter them. Could our universe be a hologram, its true code written on a distant 2D surface? Is time itself an illusion, stitched together by conscious observation like a fragile tapestry? Or are we caught in an eternal cycle of big bangs and crunches, with each rebirth subtly reshaped by the scrambled remains of the last, the wildest part? These aren't just thought experiments. Each theory leaves faint fingerprints on the cosmos, from the eerie anomalies in the cosmic microwave background to the quantum defiance of particles that seem to remember the future. Science isn't just chasing answers, it's learning to ask better questions, peeling back layers of reality to reveal just how deep the mystery goes. So now it's your turn. Which of these mind-melting visions resonates with you? Are we accidental flickers in a multiversal storm, or architects of a participatory universe where observation weaves time itself? Drop your thoughts in the comments. We're dying to hear which timeline you think is real. And if your brain hasn't melted yet, hit subscribe for more deep dives into the cosmos' best-kept secrets. The universe is stranger than we can imagine, and the journey's just getting